Similarity between mechanical and electrical oscillations. Okay, similarity between mechanical and electrical oscillations. There is a similarity between mechanical and electrical oscillation. I discussed the equation of motion of a simple harmonic motion mechanical oscillator is given by d square y upon dt square plus s by m into y equal to 0. This is the equation of motion of a simple harmonic motion. This is the simple harmonic motion equation. Simple harmonic motion equation of mechanical oscillator. Equation mechanical oscillator. Okay. This is the equation number first, where y is the displacement, s is the force constant, of proportionality or stiffness, and m the mass of the oscillator, The angular frequency is given by omega square equal to s by m, or omega equal to under root of s by m, and n equal to 1 upon 2 pi under root of s by m. Okay. The angular, this is the frequency, this is the angular frequency, and this is the frequency. Okay. And the equation of displacement is given by y equal to a sine omega t plus phi, and where a and phi are constant, known as amplitude and initial phase angle. A is constant known as amplitude, and phi is constant known as initial phase angle. Okay. The total energy of the mechanical oscillator. The total energy of the mechanical oscillator E equal to 1 upon 2 mv square plus 1 upon 2 sy square equal to 1 upon 2 differentiate of y square plus 1 upon 2 sy square, and 1 upon 2 m differentiate of y square is the kinetic energy, and 1 upon 2 sy square is the potential energy. Where equation of motion of the simple harmonic electrical oscillator is given by where equation of motion of simple harmonic motion oscillator is given by d square q upon dt square plus 1 upon lc q equal to 0, where q is the charge, and l is the inductance, and c is the capacitance. C is the capacitance of the electrical circuit. The angular frequency is given by omega equal to under root of 1 by LC, that is angular frequency, and frequency n equal to 1 upon 2 pi under root LC. This is frequency. Okay, this is frequency. The charge on the capacitance varies harmonically and is represented by an equation similar to the displacement equation, is Q equal to Q naught. Q equal to Q naught sine omega t plus phi. Omega t plus phi, where Q naught is the amplitude of charge and phi is the phase different. Phi is the phase different. Okay. Phi is the phase different. The difference. The current I equal to dq upon dt corresponds to velocity v, equal to dy upon dt. dy upon dt is given by I equal to omega q naught cos omega t plus phi. Cos q naught omega t plus phi, the voltage across the capacitor. The voltage across the capacitor is equal to Q by C, that is Q naught by C sine omega t plus phi. Sine omega t plus phi. Both I and V, therefore both I and V therefore vary harmonically with same angular velocity omega. The total energy of electrical oscillator is the sum of the magnetic energy and the electrical energy. The magnetic energy can be calculated from the current I and potential V L di by dt across the inductance and is given by magnetic energy. Okay, the magnetic energy can be calculated from the current I and potential V equal to L di by dt across the inductance and is given by magnetic energy. The integration of VI dt, that is L di upon dt into I into dt, that is integration of Li di equal to 1 upon 2 Li square, that is 1 upon 2 L differentiate of Q square. Okay. Compare it with kinetic energy in a mechanical oscillator is given by 1 upon 2 m differentiate of y square. Thus, mass in a mechanical circuit corresponds to inductance circuit in an electrical circuit, and velocity to electrical current, Thus, mass in a mechanical circuit corresponds to inductance. Mass in a mechanical circuit corresponds to inductance L, and an electrical circuit and velocity corresponds to electrical current I. Okay, thus electrostatic energy can be calculated from the voltage across the capacitor and is given by 1 upon 2 CV square, that is 1 upon 2 C Q by C whole square, that is 1 upon 2 Q square by C. Compare it with potential energy in a mechanical oscillator given by 1 by 2 Sy square. Thus stiffness S in a mechanical circuit corresponds to 1 by C in an electrical circuit. Pauli ability 1 by S corresponds to capacitance C, or 1 by S corresponds to capacitance C. Okay. Next is role of L and C in electrical oscillator. Role of L and C in electrical circuit. Okay. An oscillating electrical circuit consists of an inductance L and C capacitance. In the electrical oscillator, it is the charge on the capacitance that oscillates. In other words, the charge on the capacitor, the charge on the capacitor, the charge on the capacitor is the harmonically varying, harmonically varying harmonically varying quantity which gives rise to electrical oscillations, electrical oscillations. Okay. The charge on the capacitor is the harmonically varying quantity which gives rise to electrical oscillations. In electrical oscillators, charge corresponds to displacement. In mechanical oscillators, okay, the inductance L is the electrical counterpart of mass M, and the reciprocal of capacitance 1 by C is the counterpart of the stiffness L. So frequency is given by N equal to 1 upon 2 pi under root of LC. We can realize an LC circuit in practice and obtain simple harmonic oscillations if the circuit has zero ohmic resistance and there is no loss of energy. In practice, however, it is not possible to have a circuit with zero resistance. Hence, energy is supplied to the LC circuit to make up for this small invertible loss by electronic devices like thermonic valves or transistors. Okay, good.